3D Gaussian Splatting, or 3DGS, has completely changed how we approach radiance field reconstruction. By using explicit geometry and real-time rasterization, it gave us a way to render high-fidelity scenes at incredible speeds. But if you've tried to move 3DGS from a research project into a real production environment, like a digital twin or an autonomous driving system, you know there is a massive gap between academic prototypes and industry-grade deployment. This is what the researchers call the industry-academia gap. In the lab, 3DGS looks great on sparse view benchmarks. But in the real world, we face three massive problems. First, resource consumption is unpredictable. Standard 3DGS uses heuristic densification, meaning the number of Gaussians, and therefore the memory footprint, is an unpredictable byproduct of training. You can't just tell the system, I have exactly 2 gigabytes of VRAM, and expect it to comply. Second, there is the sparsity shield. Most current benchmarks use sparse viewpoints. This actually rewards algorithms for hallucinating, missing structures, rather than achieving true physical fidelity. If the model guesses a wall correctly because there's a gap in the data, it looks like a win, but it's not actually reconstructing the physical reality. Finally, there is data pollution. Real-world capture involves heterogeneous sensors, different cameras, different exposures, and different noise profiles. If you just throw all that data into a model, the inconsistencies degrade the final result. To solve this, the team introduced YOGO, which stands for Only Gaussian Once. YOGO isn't just a tweak to the algorithm. It's a system-level framework designed to make 3DGS deterministic, robust, and production-ready. The core of YOGO is the Deterministic Budget Controller, or DBC. Instead of letting the Gaussians grow uncontrollably based on heuristics, YOGO reformulates growth into a budget-aware equilibrium. The system partitions the scene into spatial polygons, and each polygon is assigned a target Gaussian budget based on hardware constraints or user priority. It uses a prune-then-densify sequence. In every densification event, the controller calculates the remaining budget gap and allocates a specific quota of new points. Instead of using a fixed gradient threshold, it selects the top Gaussians with the highest accumulated gradient magnitudes. This means the final primitive count is strictly predictable. You can even allocate more resources to a specific region of interest to get extreme detail on a specific object while keeping the background highly compressed. To handle the data pollution problem, YOGO uses an availability registration protocol. This is a three-stage pipeline. First, it establishes a baseline using a primary sensor. Second, it performs radiometric registration, optimizing a per-view affine transformation to decouple exposure and sensor bias from auxiliary images. Finally, it calculates an availability score. If an auxiliary frame shows extreme non-physical transformations, meaning the sensor data is too distorted or misaligned, the system simply rejects it. This ensures that only high-quality, consistent data ever reaches the training engine. To push the visual quality even further, YOGO introduces a solid optimization suite. This includes three key technical enhancements. First, area-normalized gradient accumulation. Standard position gradients often blur texture-dense regions. YOGO normalizes the absolute gradients by the pixel footprint across views, which prevents footprint bias and preserves sharp edges. Second, they introduced pruning via maximum effective opacity. Standard pruning only looks at the intrinsic opacity of a Gaussian. YOGO looks at the effective opacity, which factors in the accumulated transmittance. If a Gaussian has high opacity but is completely occluded by other points, it contributes nothing to the final render. YOGO identifies these redundant primitives and prunes them, drastically reducing the model size without losing any visual quality. Third, they implemented principal axis densification. Instead of just splitting or cloning Gaussians isotropically, YOGO generates triplets along the major scaling axis of the Gaussian. This is far more effective for recovering thin structures and anisotropic textures common in indoor environments. But how do we actually prove this works? To do that, the researchers created Immersion V10. This is the first ultradense indoor dataset, specifically designed to break the sparsity shield. While traditional benchmarks like MIPNI RF 360 or tanks and temples use a few hundred images, Immersion V10 uses a saturated acquisition protocol. They used a massive array of sensors, Insta360 panoramic cameras, Osmo high dynamic arrays, and Share Slam Lee DAR. They employed a 6-loop trajectory strategy, traversing scenes at 3 different heights in both clockwise and counterclockwise directions. The result is a dataset with a viewpoint density, an order of magnitude higher than anything else. We're talking about 30,000 frames per scene compared to the few hundred found in academic sets. This forces the algorithm to stop interpolating between gaps and start focusing on absolute physical fidelity. In the experiments, YOGO was tested across 3 tracks: single sensor sparse, single sensor dense, and multi-sensor dense. The results were definitive. YOGO consistently outperformed other state-of-the-art frameworks like ScaffoldGS and AbsGS. One of the most interesting findings came from the roaming test set, frames taken from viewpoints that the model had never seen during training. While single-sensor models tended to overfit to the specific camera path, the multi-sensor fusion in YOGO forced the model to learn a more robust, geometrically complete version of the scene. This led to significantly better generalization and higher perceptual quality, measured by a metric called calling. Furthermore, the budget controller proved its worth. By testing different budget variants, the researchers found a clear point of diminishing returns. Moving from a low budget to a medium budget gave a huge jump in quality, but moving to an ultra-high budget provided only marginal gains. Because YOGO is deterministic, developers can now find that sweet spot for their specific hardware without endless trial and error. In summary, YOGO bridges the gap between the lab and the real world. By replacing heuristic growth with a deterministic budget, filtering sensor noise through an availability protocol, and testing everything on the ultradense immersion dataset, YOGO establishes a new standard for production-grade 3D Gaussian splatting. It moves us away from hallucinating 3D spaces and toward reconstructing the physical world with mathematical precision.